Well, yep, I'm Rick from IceCube, and I'm going to be talking about SkyDriver. So, as part of SkyDriver, we designed this general system called the Event Workflow Management System, and it goes to answer one question. That's how do we take a massive workload that consists of millions or billions of tasks, and then group it efficiently into tens of thousands of jobs. So these types of workflows can be seen in multiple disciplines, but eventually they tackle and subdivide into the smallest unit of work. So that's what we're calling an event in this case. So we see similar things at IceCube or LIGO, other astronomical observations, perhaps cryo-EM data, OCR, and Condor. So how do we use this with Condor? Well, Condor, of course, we know is great at aggregating distributed resources and orchestrating workflows, and does that very well. But it imposes a one-to-one job mapping, meaning one job does one thing, it takes one input, it gives one output. So this necessitates that the task lifetime be a good deal longer than the time it takes to start up and schedule that job. If our task is only around for a couple minutes and startup takes 10 minutes or so, then we're not really going to scale well, especially to the sizes that we need. So that's what we see with events. Events, if you see the image here, take a much smaller amount of time, though they are computationally expensive. So we're going to have a different solution for that. And at IceCube, we have a very specific use case for this, why we need these millions or billions of tasks. And that's when we detect a neutrino. So a neutrino comes from a galactic origin in deep space. It goes through the Earth in some cases, goes out through the South Pole, and it's detected here in our detector, at which point we need to ask, where did that come from? And we need to know that extremely fast so we can tell other observatories around the world to point at that thing in the sky to figure out what exactly is that. In astronomy, as I know some of you realize, you can't replay things in an experiment. We have one ongoing experiment, and the thing that exists in the sky might not be there for too long. So in order to figure out where in the sky that thing came from, we reconstruct a sky map. And the sky map is a pixelized form of the night sky into hundreds of thousands of pixels of regions. And we use physics methods to calculate the probability that each pixel was the origin. So essentially, it's a probability heat map. And we've been doing this for a while. Several years ago, we created the original SkyMap scanner, and it was functional, and it did in the following way. So first, we would preempt our Condor node so we have that immediate availability. Next, we'd generate our hundreds of thousands of events. We would group those events into thousands of objects, and then those objects would get shuffled to one job each. In other words, each job is tackling multiple events. We submit that onto Condor, and Condor runs our jobs for us. Then we wait and we wait for every job to finish. We collect back all of our bundles of outputted statistics, and we assemble our resulting sky map. And it produces the most probable location, along with an error, the physics error. And that works fine, but there's a big problem with it, and that can be wrapped up into three false assumptions. So one, that we know how to group those input events. We don't, because we have a heterogeneous pool. We don't know what that pool is going to look like every time we use it, and it's finite in size. That task processes will never fail. So CPU crashes, of course, happen. So can you imagine what happens if the very last event in a group fails? Then we're going to have to replay the entire job. So maybe a scan that was supposed to take 15 minutes, if nothing failed, now it takes 30 because we have to replay the entire thing. And no one's going to be mad when we take away their compute resources because the neutrino came. They're going to be very mad at us, especially right before a physics conference. So we apply our EWMS design and we invented SkyDriver. So SkyDriver uses that design, of course, with a few domain-specific add-ons, which I'll mention. And the tasks that occur are SkyMap scanner tasks. So all that physics. So very briefly, let's see, a user will grab their neutrino object. They're going to throw it into SkyMap scanner, into the SkyDriver, and say, hey, I need a new task. The workflow management service says, okay, I can take that request and I'll turn it into a workflow. The WMS says, okay, well, I'm going to be moving a lot of data here, a lot of events, so I need to make sure I have the bandwidth for that. So it talks up to the data distribution service, who's in charge of the message queue. And I'll talk about that later. And then a channel opens up to SkyDriver where it can upload those events like pixels. At the same time, the task management service starts up on our Condor access point that says, okay, I got a workflow. Let me translate that into Condor speak. Condor does its thing. And we start up a task pilot. I'll be talking about that later on the worker. And the worker retrieves those inputted events, does its physics, and outputs one by one as soon as possible the results through the queue so that the SkyDriver can assemble that SkyMap. So how do we do this? How do we get Condor to support these multiple events in this new type of pattern? Well, there's a few guiding principles that we can follow. So first up, we want to complement Condor's capabilities. Condor thrives in a heterogeneous dynamic pool, and so do we. We want to support scientific reproducibility along the way by building a robust and repeatable system, making sure we can get stable results and we're not affecting the science. We want to design a service-first approach. So building a platform, not just an application for IceCube, but something that can be applied in other disciplines as well. And if we can, we're going to try to make everyone happy. So how do we go about that? How do we work with heterogeneous clusters? Well, Condor gives us a few good hints. It even calls them exceptional features in the manual. They can be paraphrased as guaranteed execution, extreme scalability, parallelization without reimplementation, success in heterogeneous environments, and it is adaptable to user requirements. So we're going to keep this in mind as we build up this type of design. So let's get dynamically allocated inputs and outputs and tasks onto one worker. So the file transfer system is not going to work for us in this case. We're going to have to try something else. And that something else is message passing. So by equipping message passing, we're able to separate event IO from the traditional job mechanics. This allows us to get those additional inputs over time. It also allows us to relay our outputs immediately out. And very importantly, it doesn't care about fluctuations in job count. So our work can get done no matter how many jobs we have working. If it's very small or very large, our job will still get done. So perhaps we can even manually increase that number to get a faster output. So there's a few decisions in choosing this message queue protocol, and I'm reminded of the apartment move that I know many of us saw a couple weeks ago, a couple blocks from here. And I don't exactly know the story, but I do know one thing, and it was that it was very expensive to move something like this. So just like that, it would be very expensive to change our message queue protocol after the fact. So we decided not to choose one. We built a flexible interface underneath so we could slot in RabbitMQ or perhaps Apache's Pulsar or Nats.io or maybe a future message queue protocol in the future. Okay, so big slide. We do this with pilot-based workers. So it's a lot of layers of abstraction here. I'm going to go on the bottom first. So first is backward compatible. A lot of our physics algorithms are reading in files and writing files. And it's very important to us to keep up this pattern so we can actually get user adoption. We don't want physicists having to worry too much about the platform. We want them focused on the physics, on the science. So events come in through the message queue. The pilot takes them. It transforms that into a file. The file is given to the task process, which does physics, outputs a file. The pilot takes that and throws it into another queue. And all of this is happening on a worker node. And then multiple tasks will start up afterwards, or perhaps concurrently. Through this design, we get resilience to CPU crashes through our act last and fail fast paradigm, which means we're only going to acknowledge that we received an input event when the task is actually done. So that allows the CPU to crash halfway through to get silence, radio silence, but the message, the input event will be delivered to another worker, and then we can restart. So we don't lose the progress that we had along the way. So how can we be assured that we're not affecting the science with our software? Through this, we did versioning and containerization. So we find it extremely important to document the version identifier along with the analysis results, so we can actually answer the question of what software was used in this analysis precisely. Not just SkyDriver, not just SkyMap Scanner, but a version, and then from there we can get dependencies all the way down. We want to be able to limit what all can affect the software. So we need to know that what we're testing is actually what we're using in production. So we're using containers for this and testing a realistic environment. Just like the NASA wind tunnel tests a realistic environment, we're going to be using containers to do the same thing with our software. And just for SkyDriver, we put everything in a centralized database. We throw the startup parameters, user-defined tags, so they can find their stuff later without just IDs, metadata, and those beautiful sky maps as well. They all get thrown into a SkyDriver database, so they're in one place. We made sure to include users throughout the process, so we didn't spend too much time designing without an actual problem, which means we created several Slack channels so we could actually communicate to see what's working, what's not working, what's wanted, what's not wanted. We had an open beta testing period, Q4 of last year, where we pushed towards and said, hey guys, we have a lot of new tools coming. We need to make sure that they're using realistic data. Throw everything you've got at them. Let's see how it works. And at the end of last year, we rolled it out, and it's currently connected to our data processing. 3, we kept those users in mind along the way and said, what do they actually need to know to be successful? Now, Condor does this well, and so did we want to be. And to that effect, we knew that if our system was not simple, no one was going to use it. This is a new version of the SkyMap scanner, after all, at least to a physicist's point of view. So we wanted to give them a better option, not just a different option. So we created a REST interface that has a very friendly JSON input, not unlike Condor's. Everything's validated using JSON schema and OpenAPI. So when a user requests out, hey, I want this type of workflow, and it bounces back, they know exactly what argument they got wrong, or perhaps they missed one that was required or such. We also allowed them to use multiple different images, so they could test customizations that are upcoming without having to roll out to the full production and then find something that's wrong. So looking backward and looking forward, it's been about 2.5 years since we started this project. So how's it going? Well, SkyDriver is out. It's operating very nicely. But answering the question of how generalized a system we wanted has been difficult. There are many unique tools that are involved in this whole thing: Kubernetes, Helm, Docker, Python packaging, REST, input validation. We found out that some errors only occur at very massive workflow scales, so thousands, tens of thousands of workers. Removing tech debt from the original SkyMap scanner was very difficult. It was created organically, meaning it was a pile of scripts and it really wasn't a system. No one could really answer, how does this thing work? And very much we have a small development team. So 1.1 full-time developers. I'm a full-time developer. It's a tenth of another guy. So looking forward, we're going to be releasing a generalized EWMS. It's currently in an alpha stage right now, working with all the Bryans on that. We have automatic job scheduling that we want to implement, automatic job scaling, sorry, by detecting our resources and message queues and compute. We want to add a nice monitoring dashboard that could look really cool. And we want to explore supporting DAG type workflows and maybe even force type workflows. So in summary, we designed EWMS to answer the question of how to take a very massive load of tasks and group it into tens of thousands of jobs. We did this by complementing Condor with message passing, supporting reproducibility, putting the user first by creating simple interfaces and removing those complexities. And hopefully we made everyone happy, but at least we made a lot of sky maps. And I think they look pretty cool. So the following all helped in some shape and form on this project. Thank you.